So in the video about relative age dating, I ended up with talking about Rutherford and talking about the Curies and Henri Becquerel and the fact that they had discovered radioactive decay. So I want to go through the principles of radioactive decay and show how it can be used to determine the absolute age of rocks. So the first thing, this is a bit confusing, but let me go over it slowly and see if it makes sense to you. So radioactive decay is a spontaneous and random process. So if we have a rock with 100 uranium atoms, we cannot predict when one particular uranium atom will decay all the way down to lead. It's completely random, it's spontaneous. So when I say that, you might go, well, that's not a very good clock, right? If you have a clock that ticks every second or that only ticks in some random manner, it's not going to keep very good time, right? However, we have to look at this on a statistical basis. So statistically speaking, decay proceeds at a constant rate. So suppose we start with 10 uranium atoms, okay? We don't know when any one individual uranium atom is going to decay, but we know that after, say, 4.5 billion years, 5 of them will have decayed. So we can't predict any individual decay event, but we know that after 4.5 billion years, half of them will be gone. So that rate, that statistical rate, is called the half-life of an isotope, and it represents the time taken for one half of the unstable radioactive parent isotopes to decay to stable daughter isotopes. Because of those 2 points, because it's statistically speaking a constant rate, and because that rate is called a half-life, we can use the decay of certain isotopes to date rocks. So there are 3 types of decay. These are decay and radiation: alpha decay, beta decay, and gamma decay. Gamma radiation is a process by which an atom loses energy. It doesn't change mass or number, but its total energy is decreased. So everything in radioactive decay is basically a requirement for an unstable isotope to decay to a more stable state. So if we think about energy increase, energy decrease, these are high energy isotopes, and they want to be at rest or stable. So just like we are, um, we're most comfortable when we're at rest, when we're asleep. That's when we're most comfortable. So the same thing with these isotopes. They want to get to the lowest energy state. So they do so by decaying, and the alpha decay is basically a helium particle. It's quite large, and you can hold up a sheet of paper in front of an alpha particle and stop it, so you feel like, Superman or Superwoman or whatever. You just hold up a sheet of paper. Beta particles, well, you're going to have to be a little bit stronger, but not much. You can use an aluminum sheet, aluminum foil, hold it up, stop it. Beta particle. But gamma particles are very, very energetic, and you actually need layers of lead shielding in order to stop a gamma particle. So when people talk about the dangers of radioactive decay, they're really talking about gamma radiation. That is the most energetic form of radiation. I realize you look at this slide and you may go, oh, whoa, I didn't sign up for this. This is the derivation of half-life from first principles. And I'm not going to ask you to remember it. I'm not going to ask you to do any of these calculations, but I feel it's important to show you how scientists come up with this idea of half-life. And we know the system starts out with some number, n0. These are just simply the initial number of parent isotopes when the rock formed. And they will exponentially decay according to this equation. So the negative just tells us it's the decay. Lambda is the decay constant. That is a factor of how fast these isotopes will decay, and time is T. That's what we want, right? When we're trying to date rocks, we want to know time. So we just reduce this and we just say, we want to know the half-life. So we'll just say, okay, we want to know when that initial number is half of what it started at. So we rearrange this equation and we come up with this n of 0.5t. We have t over here, and this is our half-life. With a little more manipulation, you don't need to know this. Don't worry, it's not going to be on any exam, any quiz. With a little more manipulation, we can eventually isolate time. That's what we want to know. And we'll call it T1 half, the half-life. It's equal to ln of 2 over lambda. Lambda is the decay constant, just telling us how fast this individual isotope decays to a daughter product. ln2 is a fixed number. It's 0.693. So 0.693 divided by the decay constant gives us the half-life. Let's take a look at how a system would evolve as an example, and this will also help you with your homework in determining the age of rocks. Assume that we have an isotope X and we start off with 10,000 atoms of that radioactive isotope, and it's going to decay to a stable daughter Y with a half-life of 10,000 years. We can look at this table here and we can put in our initial amount, 10,000 parents, 0 daughters. We know that's how it formed. That's 0 age, when it was born. Each half-life, we will lose half of the parents. Those parents will transform into daughters. So after one half-life, we have 5,000 parents, 5,000 daughters. The age is 10,000 years, and so on and so forth. We can also look at this in an animated fashion, and I realize it's rather quick. We start with blue parents and they decay to orange daughters, and we can see that evolution curve from the number of parents decaying through time into daughters, and the daughters are orange. And that crossover point where the number of parents is 50%, the number of daughters is 50%, goes back to our equation. We can draw a line down. That is our half-life of 10,000 years. There are a number of different isotopic dating methods and their uses. Carbon-14 decays to nitrogen-14 with a half-life of about 5,700 years. The longest half-life here is rubidium-87 to strontium-87 with a half-life of 48.8 billion years. And these two isotopes of uranium are quite cool because 238 decays to lead-206 with a half-life about the age of the Earth, 4.5. And U-235 decays to lead-207 with a half-life of about 704 million years. What's really good about this, what's really useful about this, is that 238 and 235 typically occur together in the same mineral. So we have two independent clocks in that mineral keeping time. And if everything is hunky-dory, those two clocks should match. So it performs a check on the radioactive systems. There are assumptions in radiometric dating. And these are important. And these are things that you may say, oh, wow, how do we check this? And the nice thing is that geologists understand our assumptions, and we understand how to check these assumptions to make sure that they're met before we publish any age. The first one is that the system remains closed during the time period of interest. That means when a parent decays to a daughter, that daughter and parent remain in the system, right? We have to count how many parents, how many daughters in order to get an age. If a daughter leaves the system or parent enters the system, we have a problem. So we need to check that. So that means there's no daughter gained, lost, or incorporated into the rock at the outset. There is also no parent gained or lost, and the decay rates are constant, that they don't change through time. And there are some Very interesting implications for people who say, well, what if decay rates were faster in the past? I'll give you the simple answer. If decay rates were faster in the past, the Earth would be much, much, much hotter. And in order to fit, so for example, if we use that old estimate of 6,000 years for the age of the Earth, if we say, okay, let's fit all that radioactive decay into 6,000 years, I hate to tell you this, the Earth would still be completely molten. Um, so we have a pretty good idea that these decay rates are constant. So with carbon-14 dating, it's not a usual geology tool, although it is used for much younger rocks. And the reason is it's only useful on organic matter. As material becomes older, then recent contamination becomes problematic. The half-life is 5,700 years. So if you remember that decay curve, you quickly lose carbon-14 in the system, and it after about 50,000 years, some people can push a little beyond that. But after 50,000 years, you basically have no carbon-14 left, and it's easy for small bits of contamination, of organic contamination, to disturb the system. How does it work? Well, as we breathe, as we're living, we're breathing in carbon-14 as part of the atmosphere, and it's incorporated into living tissues. But because we're alive, we're also breathing it out. So that means the system is not closed. And remember, the assumption of radiometric dating is that the system remains closed. So we're breathing it out, the system is not closed. Now, the minute the organism dies, all that carbon-14 that's incorporated into that organism is now locked in. There's no more exchange of that carbon-14. So it then begins to decay. And there are some complications to carbon-14, and you can read all about it if you want. But basically, it's a pretty good system for determining very young ages. We cannot get to the age of the Earth using carbon-14. We do not date rocks using carbon-14. We only date mostly wood particles and things like that. Okay, so you can see here, I'll show you the curve. This is the curve. Here's 50,000 years. This is the amount of daughter. This is the amount of parent. And you can see after really about 40,000 years, but certainly by 50,000 years, we're almost out of carbon-14. That's what makes it problematic for anything beyond about 50,000 years, although there are some new very sensitive instruments, and if you have a very clean sample, you may be able to push this back a little bit older. So it's not used in rocks, it's not used so much for geology, but we do have other systems that we use for geological materials. So let's look at some of the information that we can get from radiometric dating. And it's cool because different isotopic systems, different isotopes become closed or open under different conditions. When they're closed, that means there's no exchange. The amount of parent in there is locked in. And so if they close at different temperatures, then we might be able to use that. Different minerals within the same rock also close and open under different conditions. So that information, all of it, is useful in determining the history of the rock, depending, of course, on the rock that we're looking at. So types of rocks that can be dated, well, we can date igneous rocks. We can date pretty much all types using multiple methods. Metamorphic rocks, we can date most types, multiple methods. Sedimentary rocks, those are a little bit more limited, but we are in the process of developing more sophisticated and useful methods for dating those sedimentary rocks. Let's talk about the dating of igneous rocks. Igneous rocks are formed from molten magma. If it reaches the surface, we call it lava. And we may want to know, how old is this lava? How old is this igneous rock? There are different size bodies of igneous rock, which makes this a little trickier. And small bodies, and we call them dikes, sills, and stocks, they cool quickly. They may cool on the order of a few days, a few weeks, even a few years, which in geologic time is not much at all, whereas much, much larger igneous bodies, batholiths, will cool much more slowly. So we have to ask the question, what is it we want to know? So an igneous rock will remain an open system while it is in the fluid state, the magma state. Think of it as the same as carbon-14. We're breathing it in, we're breathing it out. These igneous rocks, when they're molten, they're incorporating parent, they're losing. So it's an open system. And so we have to ask the question, what is it exactly that we want to know about this particular igneous rock? We have found our igneous rock, and now we have asked the question, and the question is, what is the crystallization age? When did this molten rock become solid? In this case, we're going to use the uranium lead method. That is a preferred method by geoscientists across the globe because the system is robust, it's very hard to disturb, and because the system produces ages that are very precise and have small errors. So when dating igneous rocks, we want a mineral that will not lose parent, that will not lose daughter, at least not readily. And that preferred mineral is called zircon. I show here numerous pictures of zircon. These are under specific microscopy, scanning electron microscopy, normal light microscopy, and so forth. Just different images of zirconium. The interesting thing about zirconium is that uranium 235 and U238 both substitute readily into the crystal for zirconium. They're about the same size, they have the same electrical charge, so they're easy replacements for zircon into the system. And that means that these crystals contain clocks that we can use to date the rocks, makes them very, very favorable for geochronology system. And uranium lead dating, we call it concordance, makes use of the fact that 235 and 238 are both radioactive but decay at different rates. I mentioned this earlier. 238 decays to 206 with a half-life right about the age of the Earth, 4.5 billion years. 235, on the other hand, has a shorter half-life, and it decays to lead 207 with a half-life of 704 million years. So the older the rock, the more enriched it is in 238 relative to 235, right? Because 238 decays slower, 235 decays faster. So if you start off with the same number, you're going to have fewer 235 than you are 238 after a certain time. And that dual system provides a check into the assumptions of any parent and daughter loss. So let's look at how that happens. So we have an idealized curve called a Concordia plot. And it's just simply looking at, you can see here's 236, 238, here's 207, 235. And you can see how those ratios change the older the rock is. So if a rock is 4.5 billion years, we would expect to find more daughter in the 235 system than we would in the 238 system. And that curve, you can see how it progresses. And every place along that curve would give us an age. And if our ratio of the zircon, if it falls right on that curve, then we have the age and we have a little range of error. It's a beautiful, beautiful system. Now, suppose the system's disturbed. Well, if our zircon age falls above that line, that means it's likely to have inherited some daughter into the system, and so it can give us an erroneous age. If it falls below that curve, that means that it has probably lost some lead into the system, and we see that sometimes, and we actually know how to deal with it. It's kind of cool. So what we want to see is we want to see something that falls right on that curve. Now, when we're doing this dating, we actually want to zoom in on different portions of that curve so we can get a more exact date. So let's take a look at a real life example. This is from work that I've done. This is from igneous rocks on the Zabkhan microcontinent, Mongolia, where we were able to extract these zircons from volcanic rocks. Here is the region in Mongolia. Here are igneous rocks. This is a rhyolite. This is a basalt here. We were able to extract zircons from this rhyolite. We were able to date them. So now all I've done here is I've blown up that curve, right? We saw that big long curve from 0 to 4.5 billion. Here I'm just looking at a very small interval of time because these ratios tend to be very, very tightly constrained. And we can see when we average those, we get an age of about 795 plus or minus 8. So this is a beautiful example of a concordant zircon giving us a very good age. Now, what happens if concordant ages are not found? Well, if they're not concordant, then it's likely that lead loss has occurred. It's far more common than gaining any uranium. Does it make the age useless? Well, it could, but there is some information that we can glean if the lead loss is fairly consistent. I'll show you how we do this. So what happens to zircons during a disturbance? And the disturbance is typically metamorphism. So we can see here that lead can be lost during this disturbance. And so the crystals will evolve. They'll lose lead at variable rates, beginning at the age of that they crystallize. So in this case, it's hard to see, but it's 2.5 billion years. And they will evolve and they will touch the other end of Concordia at a younger age, which here is about 750 million years. So it gives us, this actually gives us, if it's a nice line, it actually gives us two information. It gives us the age of crystallization and the age of the metamorphism that disturbed the crystal. So if we look at this out of animation, we see these crystals here. We see an upper intercept at 2 billion, a lower intercept somewhere here, say, let's say 250 million years ago. So we have the age the rock crystallized and we have the age of the metamorphism. So that's kind of a useful information. What causes it is typically metamorphism, and we have to, of course, keep in mind the history of the region. Another tool that is used commonly in geology is potassium argon dating, and it's particularly useful for looking at these big, big igneous bodies because different minerals, for example, hornblende, biotite, and feldspar, they all close at different temperatures. So hornblende, for example, closes at 500 centigrade, biotite at 350, and feldspar between 100 and 200, depending on the size of the crystal. So here are these minerals. This is feldspar, this is biotite, this is hornblende. And again, like uranium lead, we want to know if parent or daughter is lost or gained. And we typically have applied a variant of the potassium argon dating called argon argon. Again, I'm not going to go into this, but this system, this method of dating rocks provides a check on our assumptions. So how does it do that? Let's look at a real life example from the Majaguan kimberlite of India, and then we'll look at a disturbed system from Madagascar. So here is an argon-argon age from the Majaguan kimberlite. And you can see here that we actually date this mineral a number of times. So what we want to see is we want to see that all of those ages agree all the way across. So we actually are heating this step by step. And if we get this nice flat spectrum, that tells us that the system has remained closed, that there's no argon or there's no parent or daughter leaving and entering the system. So it's a closed system. This is a good age. Now, here's a very bad age. And here we can see that every step we go, we get a different age. And so if we just said, okay, well, let's just average it all together, we would get an age of 1.9 billion years. But we can see this system is disturbed. And the lowest ages would be about 600. But this is, when we see this, unfortunately, we just go, a lot of work for nothing. Okay, but it tells us that the assumptions that we made in radiometric dating in this case did not hold up. And that happens. It's a natural system, so no big deal. What about slowly cooled rocks? Let's take a look at a big granite pluton that takes millions of years of to cool, and we want to know how fast did it cool. Well, here's another real life example. This is all of these are from my work. This is a carry-on Pluton near Antananarivo in Madagascar. It's a granite. It contains zircon, uranium lead, contains hornblende, biotite, case bar. So we can get ages from all of these. We know they're all close at different temperatures. And when we do that, we can look at the data. The zircon age gave us 532. That's the age that it crystallized. Hornblende 512, biotite 478. One of the case feldspars 435, the other one at 410. So you can see this exactly as we would expect. This one's a high temperature closing. This is the next highest. This is the next. These are the two lowest. So perfectly in line. And these are the data, but we can put them on a graph and we can then estimate the cooling age of that Pluton. So it's really cool. Dating metamorphic events, same systems we can use to date metamorphism. Sedimentary rocks, we have a little bit more problem because sedimentary rocks don't form with radiometric clocks set at 0. They actually incorporate, they're just dirt, right? They're washing away in rivers, so they can carry zircons, they can carry all kinds of materials, very tough. In some cases, sedimentary rocks will incorporate small amounts of new radiogenic material, and we may be able to date that to get the age of sedimentary rocks. There's a new technique looking at uranium decay chains in limestone. It's lead dating. It's just another variety of uranium lead. It can work. It often gives huge errors. It's a developing technique that may prove more, is proving more and more useful as we refine that technique. Detrital zircons, this takes advantage of the fact that sedimentary rocks typically incorporate zircons from everywhere around them. So what we can do is we can look at the oldest zircon in the system, and we can look at the youngest zircon in the system, and we know that the rocks must be older than that youngest age that we observe. So it's not particularly useful. Here's a real life example. And we can see here that the youngest zircons in this Vindian Basin are around 1 billion years. So we would say that the rocks they have to be older than about 1 billion years. Okay. More interesting is something called xenotime, which is incorporated and found as an overgrowth of cement in sedimentary rocks. And that can actually